Alright, hello. Here we have the very first lecture of quantitative reasoning. And the first unit of quant is going to be pretty interesting. It's going to be over sets, logic, and unit analysis. And we'll begin with sets, which begs the question, well, what is a set? Besides something I need to do more of at the gym, a set is a collection of distinct objects called elements. And we typically denote a set with these squiggly brackets. So here's an example of a set. Here's a set of three colors, red, blue, green. Here's another set. 1, 2, 3, 4, and so on. It's a set of counting numbers, or what we know as natural numbers. So as you can see, we have finite sets and infinite sets. And just know that order doesn't matter. So the set of red, blue, and green is the same thing as the set of, green, red, and blue. More on equivalence later on in the lecture. And we want to go ahead and get some notation out of the way. So that symbol that looks like a C with a little dash in the middle means is an element of. So for example, 7 is an element of the set 1, 2, 3, and so on. Or you can also say red is an element of the set of red and blue. So that symbol there just means is an element of. And there's another set that's of particular importance known as the null set. The null set is the empty set, contains no elements, and it's denoted as you see there. And cardinality of a finite set is just the number of elements in that set. And it's denoted with those absolute value bars. So we can see in example number 1 here, the cardinality is 3. Here the cardinality is 4, because there's 4 elements in that second example. So let's talk about comparing sets. So let's look at disjoint, overlapping, and subsets, let A and B be sets. So first thing we're going to talk about is what it means to have a subset. So a subset is denoted as such. That's the symbol for subset. And this is saying A is a subset of B. And what this means is every element from A is in B. So A is a subset of B because it's completely contained inside B. So if we were to draw a diagram, if this were set A, then there's set B. Or another way of looking at it is A and B are the same sets. Is another way of looking at it. If A is completely contained inside B, then it's a subset. Now, a proper subset is denoted as this. And for a proper subset, A is a proper subset of B if every element from A is in B and A does not equal B. So proper subsets means A is truly, completely contained inside B, and they are not equivalent. So technically every set is a subset of itself, right? Because the element of every set is contained within itself. Well, this isn't very satisfying, so if I have a proper subset, every element from one set has to be contained in the other, but not quite be equivalent. What it means for two sets to be equivalent means they're subsets of each other. So A is equivalent to B if A is a subset of B, and B is a subset of A. So naturally, if everything from A is inside of B and everything from B is inside of A, well, then they must be equal. And disjoint, so there's no notation for that. We just say two sets are disjoint if they have nothing in common. So A and B have no elements in common. So diagram would be just two completely separate sets. And then overlapping, all that means is A and B have at least one element in common. Perhaps more, but at least one. Alright, let's go ahead and look at an example. So let alpha be the set 1, 2, 3. Let Bravo be the set 3, 1, 2. Let C be the set of natural numbers. Let set D be red, green, blue. Let's answer some true and false questions. So number 1, is C a subset of A? So is everything from C inside of A? And the answer is false. If you look at set C contains numbers like 4, 5, 6, 7, and so on, and those are not inside of A. So C is not a subset of A. Is A a subset of C? Well, that is true. If you look, everything from A is also inside of C. Alright, and then example number 3 is A equal to B. True. They are equal to each other. That's because everything from A is inside of B, everything from B is inside of A, so as you can see the two sets are equivalent. Number 4, B and C are disjoint. This is false. They have elements in common. Number 5, A is a subset of B. That is true. Everything from A is inside of B. Number 6, this is a proper subset notation. So you need to pay attention to that. Is A a proper subset of B? And no, it's not. Everything from A is inside of B, but they're the same set, essentially. So they're not proper subsets. Alright, so with that lingo out of the way, let's talk about some Venn diagrams. So Venn diagrams are very great for representing sets. And in this example here we have a data set, pass-fail for students that completed the test review and those that didn't. So due to the complementary nature of the sets, a Venn diagram is perfect for this data set. So let's go ahead and make a Venn diagram for this set. And basically put everybody who passed in this circle and everybody who completed the review in this circle. Alright, so if we see there are 19 students that passed and completed the review, 3 students that completed the review but did not pass, and then 7 students that passed but did not complete the review, and then that just leaves 11 who neither passed nor completed the review. So there's an example of a Venn diagram for this data set. There's actually 4 acceptable answers. Just be careful that your Venn diagram makes sense. You don't want to over-label it, and you want to keep it nice and clean. Alright, so last subsection for the first lecture. Let's talk about unions, intersections, and complements. So the union of two sets contains all the elements from either or both sets, and it's denoted as you see there. So in other words, one way of looking at it is A union B equals the set of all elements X such that X is an element of A or X is an element of B. And the key word there is OR. So OR is associated with union. So it's basically combining the two sets. So let's look at this example. Let A be the set 1, 2, 3. Let B be the set red, blue. Then their union is just going to be the set containing all of it. 1, 2, 3, red, blue. That's basically what a union is. Now an intersection of sets A and B, denoted as you see there, is the set of all elements contained in both A and B. So in other words, A intersect B equals all elements X such that X is an element of A and X is an element of B. So all elements in the intersection have to be contained inside both sets. So in other words, it's where the sets overlap. So the intersection is where the sets overlap. So if we look at this next example, A intersect B is going to be where A and B overlap. So we can see, looking at A and B, the only place they overlap is on element blue. That's the only thing they have in common. That's what the intersection is. So the intersection of two sets is essentially the set of all elements that they both have in common. Now, before we talk about the complement, we have to introduce the universal set. The universal set is the set containing all elements, and all sets are subsets of the universal set. So basically, the universal set is just setting some parameters. It's the universe in which you're studying. And the reason the universal set becomes relevant is when discussing complements. The complement of set A, denoted as you see there, is all elements not inside of A. So the complement is everything that's not in that set. So A complement equals all X such that X is not an element of A. So let's look at this example. Suppose we got a pet store, and that's what we're looking at, and the pet store has cat, dogs, lizards, and snakes. So let A be the set of mammals, and B is the set of non-mammals being sold at the pet store. And let's say D is, the set of animals that are, on sale. So the universal set is all the animals in the pet store. Let's go ahead and evaluate. So starting with number 1, D complement is going to be all elements that are not inside of D. So D contains snake and cat, so it's going to be everything that's not inside that set, which would be dog and lizard. So that's why we need the universal set. Basically, the complement is going to be everything in the universal set not contained inside the aforementioned set. So D complement is every element that's not in set D. All right. Let's go ahead and look at A union B. So that's just going to be cat, dog, lizard, snake. Now you may notice that this is equivalent to the universal set, so another correct answer, you could just call it U. Let's look at A intersect B. If you look at A intersect B, hey, what do A and B have in common? The answer is nothing, the empty set. There's no overlap between set A and set B. Set A is cat, dog, set B is lizard, snake. They have nothing in common. Let's look at A intersect D. What do A and D have in common? Well, they both have cat in common. So that clarifies that. Now, let's look at example number 5. So we'll go off to the side here and do A complement. So off to the side, A complement is going to be everything that's not in A, which is going to be, well, lizard and snake. Cool. So we want to figure out where A complement intersects with D, and the answer is snake. Because that's the only thing A complement and D have in common. Alright, and then the last one, we want to do the complement of the intersection of A intersect D. So off to the side, A intersect D, we did earlier in example number 4, is cat. So the complement of that set is basically all the animals except for the cat, which is dog, lizard, snake. Alright, I'm done with that. Alright, cool. So that's that example. Let's go ahead and practice with some more Venn diagrams and do some shading. Looking at number 1 here, we got A intersect B intersect C. So we got our first triple Venn diagram. So it's just the intersection of A, B, and C, which is right there in the middle. So we just want to shade the only place where all three intersect. Alright, and then let's go ahead and look at number 2. So this is the complement of the intersection. So the complement is, shade everything except for where A and B intersect. So it's going to look like this. There we go. So basically, that's the complement there. Basically not shading the intersection. And let's go ahead and look at this next one. So this one's a little bit trickier. So looking at number 3, so this is the complement of A intersect B. So that means is do not shade A intersect B where they overlap. And we want to figure out where the complement of A intersect B intersects D. So anything we shade must be inside D as well. So we need to shade everything in D that is not inside of A intersect B. So everything in D that is not in A intersect B. So that section is in D, but it's not in the intersection of A and B. This sector is in D and not in the intersection of A and B. And then all this sector is in D, but not in the intersection of A and B. So here's the answer here. Alright. Let's go ahead and look at one last example here. Use this Venn diagram to answer the questions. So here, well, we have a Venn diagram representing the number of people that use Facebook, Twitter, and Instagram. So question 1, how many use Facebook? So there's basically we take all the data from the Facebook circle, which is 3, 5, 7, and 20, and add that up together, and that's going to be what, 35, I believe. Yep, 35. So in this data set, there's 35 people that use Facebook. Now the next question is how many use Facebook and Twitter. So and means the intersection. So we're taking everything from the intersection of Facebook and Twitter. So that would be 5 and 7. Because that's where those two circles overlap, giving us an answer of 12. Now or, so remember and is associated with intersection. Or is associated with union. So how many use Facebook or Twitter? We'll take the union of those sets and basically just add up all the numbers from both sets. So in the Facebook we have 3, 5, 7, 20. Then from the from the Twitter circle we already got one of the 5, so we got another 5 and 6. So we're just adding up those 6 numbers. So let's go ahead and do that real quick. 10, 30, 40, 46 is the answer here. And then this last one, don't use. That's an example of the complement, essentially. It's basically add up all the numbers that are not inside the Twitter circle. So we got a 3, 20, 11, and don't forget that 2. So there we're just adding up all the numbers that are not in the Twitter circle, which is going to get us 36, I do believe. Let me double check that. Yep, 36. Alright, there's our first lecture of the semester. The book goes into greater detail on these topics, so feel free to refer to the book. If you want to know what pages this is on, it's listed in this schedule, which let me go ahead and write it down here for you. So this topic is going to be on pages 319 to 332 if you want some additional practice. And if you look in the table of contents in the book, there's a section called sets. Alright, well that's a wrap. So this covers everything that's on that first homework assignment, so you guys are ready to start that, and have a wonderful day.